In this video, we are going to discuss LLMs or large language models, the base technology that powers all modern AI chatbots that you use in your work or your personal life. If you use ChatGPT a lot, then GPT-4o is the LLM that it uses to understand what you're saying, to process that information and try to reply to you. We are going to break down in mathematical terms how that process happens, and we are going to do that all in our own playground. So here's our playground. अगर हमको ये समझना है कि how does a language model work, first we need to understand how does the language model understand what you are saying, because very clearly it doesn't understand English, Hindi and German for that matter, right? So how does it understand what your prompt means? More importantly, how does it understand the nuances of this? If I'm having fun with a friend and I tell him I'm going to kill him, right, that's a joke. If I'm in a dark alley and I hear I'm going to kill you, I need to run. In both the sentences, killing means a very different thing. But all the modern chatbots seem to understand this very simple differences very quickly. How do they do that? Here's our playground. Here I have created a small LLM for the demo purposes. I'm going to give it a tricky prompt, the bank by the river. Now here you can see bank can mean the financial institution when clearly in the sentence it means a river bank, right? Let's analyze what the LLM does. Let's give it a minute. Here we go. And here we go. Whoa, what happened, right? Let's break down what happened. The prompt included 5 words: the bank by the river, right? Now imagine a three-dimensional space, just like your 6 standard coordinate geometry, where the position of each point can be explained by 3 coordinates or 3 number values, x, y, z. Now imagine you have taken a three-dimensional space and put all the words of English language in it and clubbed all the similar meaning words together, right? Each word has its own x, y, z. The yellow dots here represent before LLM processed what the word meaning itself was. So before the LLM processed it, you will see that the word the was near there, the hun, and our, my. Bank was near banks, banking, financial, finance, cash, right? And all of that. But once LLM processed the entire sentence, right, it moved all these points to this red position, right? A very key insight here is also that all the red dots kind of merged together. Where did they end up? The ended up near river, bank, banks, rivers, banking. Bank also ended up near river, banks, rivers, banking, creek, right? Similarly, all the other words. So you can understand that what happened was the LLM took all the tokens and created a sentence and converged everything towards the common meaning of the sentence. How did it do that? For that, we need to understand the math behind how this long language processor works, which is what we are going to get into next. Now, the big question is, how did the points move, right? To understand that, you have to understand a little bit about how machine learning algorithms are made and how do they work, which I'm going to criminally oversimplify for the purposes of this video. Imagine you are an analyst that works for a company that sells butter, right? And you need to project how much butter you will sell in the next year or maybe in the current year. You will of course first take last 5-10 years of sales data and related data to the sale of the butter, like how much was sold for it from each shop, how many shops, how many salespeople per shop, how much was produced, maybe some external factors, and put it all together in an Excel sheet. And then you will start identifying patterns that maybe, let's just say, increasing one salesperson per shop increase the sale by 2%, or closing down one shop decreased the sale by 10%, right? And according to these pattern identifications, you are going to try and guess to the best of your ability from the current state of those parameters that what will the sale be for this year. Now, an algorithm works in the same way, where the actual sales value is the target, everything related to it are predictors, and you are going to give all this past data to it so that it can identify relationships between the target and the predictor to come up with like the most probabilistic value for the current year. The process of giving past data to this algorithm is called training, right? And that is how all machine learning algorithm works. Now, let's think about our language model in the same context, right? But here there is like a key difference. Here we have to train it on language, because on a very base level, every language model is a completion algorithm. It basically is taking your prompt and trying to predict what should come next, what is the next word or the set of words that is going to complete this prompt. So, in that context, given language, it is very tricky to train an algorithm, because there are like multiple complexities that comes when you are talking about language. Of course, the first one is vocabulary. How are you going to quantify the meaning of language or words in that language? Like, what does cat mean? What does mat mean? What is bank? What is river? What is the? What is right? Stuff like that. Because you can't really give literal language to the machine to train on, because that it will not be able to understand, right? So we need to somehow quantify meaning of each word. Then of course, word order. When you are speaking something, right, you can use the same set of words, but the position of those words can change the meaning entirely. Dog bites man and man bites dog are two very different headlines, right? And then of course, and which is the key innovation that changed the AI chatbot game entirely, was context. Context quantification is a very very important step, because everything that you are saying is coming from an overall context of the sentence or the paragraph or in a situation that you are saying it, right? Just like in our example, bank is not financial institution but a river bank, right? So somehow the machine needs to understand that also. How are we going to quantify all this so that the algorithm can actually understand it is something that we are going to get into next. So let's now see how do we solve the language problem, right? Our problem at hand is somehow, the first problem of course is vocabulary, right? How do we somehow quantifiably represent words and their meanings? So first thing is that we have to represent words. That is a process called tokenization. What happens in each large language model is that we create a vocabulary bank that we can assign individual numbers to. And this process is called tokenization. Like in our LLM, currently the prompt that we have used, the bank by the river, the is represented by 1996, bank is represented by 2924, and buy is represented by 2011. Now all of these are IDs, right? Now you the important thing to note here is that tokenization is a field of study of its own, with multiple innovations that has happened over the course of last few years. And GPT uses byte pair encoding, where you don't necessarily uh, save every word as a token. You can save, let's just say, a word today as a pair of day and two, which are individual tokens, but you don't necessarily have to save today, right? So you can get into it more deeply, but for our purposes, you have to understand that there is one individual identifier for each word. Now, we cannot expect only one number to represent all contextual and semantic meaning of a word, right? So we need something that is heavier, which is vectors or embeddings. If you remember, as I said in my first example, in this 3D visualization, each word was positioned in a three-dimensional space, and its position can be explained by x, y, and z, right? That value of x, y, z is what we call embeddings, which is basically representing or clubbing together similar meaning words in a more contextual way. Now, in a real LLM, it can never be three dimensional because of the size of the language and the variability that comes with language. Like the local LLM that we have developed for this video uses 384 dimensions. That means each individual vector for each word has 384 numbers representing their position in a high dimensional space. You have to understand that in a production kind of a use case where you when you chat with ChatGPT or Claude or Gemini, whatever you use, these can go up in thousands, 16, 15,000s, right? Just so that they can densely capture what every individual word in what context means, right? Now, if we have somehow a unique way to represent or identify a token and somehow represent its meaning, the next problem is, of course, the order, right? Our example of dog bites man and man bites dog, right, is where we have to somehow establish that these two sentences are different. So this is where positional embeddings come in. So if you have given a sentence of 5 words, there are 5 particular indexes. We are going to define a positional embedding which is of the same size of the actual embedding. Let's just say if we use 384 numbers to represent the word the, we are going to use 384 numbers to represent its position in the sentence, and we're going to add it. Now, from a very numerical perspective, right, the man bites dog and dog bites man becomes different representations. This is how we establish uniqueness in a LLM.
So far, we have quantified tokens, their meanings, their positions, everything, right? Now, for the main event, how are we going to quantify context? This is where self attention comes in. The revolutionary idea suggested by the paper released by Google in 2017, titled Attention is All You Need. If you are really interested in this, you should take a look at this paper. This paper established the transformer architecture, which is the base technology which is used by all the modern LLMs, right? The core mechanism of self attention is basically a series of mathematical steps in which each token looks at other tokens in the sentence and identifies what is their relationship with them, right? So think about it in this way. We are going to calculate three new vectors now. One is going to be query, or what I am looking for. Each token is going to ask, what am I looking for? Let's just say bank is going to ask, I need a little bit more context to understand what am I suggesting, right? Key. Key is the value that every token broadcasts, that how, what am I providing? Let's just say river is providing water level context, right? And value is what the actual embedding is. Now, to do this, what we are going to do is we are going to calculate Q by multiplying the embedding value that we saw is a 384 numbers long, but by a matrix which you can imagine as like a big meaning matrix which holds all contextual relations between all words ever. For this LLM, so every LLM will have one WQ, one WK, and one WV matrix. Now, to get a Q value, we are going to multiply embedding with WQ, K with WK, V with embedding into WV. This is going to return to us new vectors. Every token now get their own Q, K, and V vectors, right? That is step one. Step two, we are going to now use these vectors to calculate attention scores. Attention scores is nothing but token asking who should I attend to the most, right? For this, we are just going to do Q into a transpose of K, which is basically making the vector vertical, so that it gives you a proper dimension, divided by root 64. Root 64 just so that the value doesn't blow up into some unrealistic number, right? and it is going to give you this matrix. In this matrix, you can see that bank has the highest score with river. This is because, of course, bank's major context is being drawn from river, right? The step 3 will be softmax normalization, which is nothing but uh, scaling this so that every row sums up to 1, right? Now, this is exactly why your points moved. Token bank has a query that I am ambiguous, I need some context. Token river has a key, I provide nature and water context. A high attention score, bank pulls meaning from the river's value. Output embedding for the bank now contains water related information. The point physically moved towards water in the words of embedding space, right? Now, how do I compute these new representations? I am going to take every vector and multiply its embedding value. I'm going to take every embedding and multiply it with the attention scores that I got up in this matrix, and every token is going to now get its own new vector which is more converged towards the common meaning of the sentence, right? So now the new bank vector is going to understand water related context. This is exactly what happened here. If you see, bank was before near banks banking, etc., etc. Now it is near river banks, rivers banking. So once I have this, right, this is only one head. This is a key caveat that you have to understand to understand actually the scale of calculation that is happening when you are giving any LLM a prompt. This is one head is going to only capture one type of relationship. We don't really understand or can know what each head did, but let's just say in our model we have 12 heads. Each head is going to do this operation over and over again, right? Let's just say head 1 established syntactic relationship that the is pointing towards the bank, and the noun that is being addressed by this article or this verb is addressing this noun, stuff like that. Maybe like the head 1 established grammatical relationships between the tokens. Head 2 might understand more semantic understanding. Let's just say water related context is important to understand bank, stuff like that, right? And these 12 heads worked in parallel, right? And they all gave a 32 number long vector, right? 32 into 12 gave us the new sentence vector of 384 dimensions, which is what we originally had, right? Now, this particular multi-head process is going to happen over multiple neural layers. Now, this is where it gets a little bit complicated. A neural layer is a machine learning algorithm in which you can take the output of a layer and feed it and feed forward it to the next layer so that it can do the same process but understand a little bit more. So let's just say your multi-head layer 1 established bank starts noticing that river exists. Layer 2, bank pulls more meaning from the river. Layer 3, a relationship between all words are strengthening. Layer 4, higher level patterns emerge, right? Layer 5, abstract meaning crystallizes. And of course, layer 6, bank now fully understand that it is a river bank, right? Now, this is something that will happen over layers, and this is exactly how human beings also sometimes process things, right? This is where we are mimicking digitally or computationally what a human brain does. So if you see, each layer moved the words around a little bit according to whatever it was establishing, right? Layer 1 moved this a little bit, layer 2 moved this a little bit, and it explored the higher dimensional space to get to a common understanding of what the prompt actually is intending to do. This is what self-attention is. This establishes a context aware mathematical formula on which transformer is going to work on. When we clearly understand how we are translating language and its meaning into mathematical formulas, right? Now we have established the transformer, right? We have established all the things that we need, but we have not trained anything yet, right? So the idea is that up until a up until a point an LLM is trained, all of these values are random. Like all the token embeddings will hold random numbers. All the weight matrices which understand contextual relationships are going to be random numbers. You can imagine, if you have to visually, like all the tokens like lying somewhere in one place, right? Or arranged randomly, something like that. What now, in training we are going to actually teach the model what language means. How are we going to do that? We are going to do that by running a loop of the same self-attention mechanism, but with known examples and billions of examples, right? Let's go with this example. The bank by the river, the next token, ideally in my data set, should be should be flooded, but the model predicts closed, right? Very clearly, this is the first example. The model will be like, okay, from whatever I understand, the next token should be closed. But but the known right answer is flooded, right? What it is going to do then is that it is going to calculate loss. The loss is basically what is the actual difference between the flooded embedding and closed and the logarithmic value of it, which is going to give them a functional loss value, which let's just say is 4.6. I can mark it can be different values, but let's just say in our model it is high loss, right? So if it is high loss, what it needs to do is that it took the token embeddings, it multiplied it with positional embeddings, it came up with a vector, then it went into the self-attention mechanism, then it did the calculation steps, right, from the weight matrices and everything, and gave you back closed. Now it is going to run a loop backwards to correct itself. It is going to take that loss value and run back into the neural layer for 6 layers, and is going to keep adjusting whatever it is that is required to get the answer to be flooded. This is how it learns context. This is how it learns meanings. It is going to keep updating the weight matrices values and token embedding values till the time the calculation answer becomes flooded. This is what training is going to look like, right? It is going to update the weights, it is going to update the embeddings. And by the end of it, there will be big three matrices. One WQ, which let's just say for our purposes, now understand that when I am getting a token bank, right? I need to generate a query that searches for disambiguous context, because bank has multiple meanings, right? WK learns that when I am river, I need to generate a key and look for a key value for other tokens that are looking for disambiguous context, right? WV learns that when I am river, I need to generate a value that gives out water related information. This, once trained, gets frozen. So this is exactly why we call GPT is called generative pre-trained transformer. Because once the training stops, it is the model itself is not going to train. You can keep chatting with it, but whatever you are saying is not going to update its main understanding, right? So it is going to always remain frozen, or at least up until the point of time I'm making this video, there is no new algorithm that is going to update the understanding. While Google has come out with a new paper called nested learning, that is something that we are going to break down in our next video. Once this has happened and we have created a pre-trained transformer, this is what is going to be exposed to the users. who are going to give it prompt and ask it to like do stuff. But that's the key. We never ask any of these any of these products for a completion task, right? We don't ask it to complete our sentence. We give it very complicated task. We ask it to uh, run or write code, create documents, to give presentations, to do complicated stuff, right? How how does this do that? Because it's very clear that like whenever you are giving, let's just say, a 20 token prompt, you are going to give it from whatever I have explained now, it should just give you back a response. That's it. But it doesn't do that. It goes on and does all the multi-step stuff where it is going to figure out, okay, it needs a document, it is going to figure out it needs something, some permission accesses, it is going to figure out it needs new information. Because because you have to keep in mind that 2023 was the time when training stopped. So for all the new current information, the the model itself doesn't really have knowledge, right? But you keep asking it to do very updated tasks. How does that? How does it do that? Right? That is where reasoning agents come in. You, for your understanding, when you are talking to ChatGPT, you are not technically querying GPT 4.0, which is the base model which is being used. You are not directly giving a prompt to that. You are giving it to a reasoning agent which ChatGPT has created in between. So let's just say I'm going to give a prompt. This is ChatGPT API. I'm going to give it a prompt that is going to ask it what is 15% of population of Tokyo. Just You see, what happens is that it takes your prompt and it breaks it down into other prompts. What the reasoning agent does is that, let's just say, what is the first thought? To calculate 15% of population of Tokyo, I need to know the current population of Tokyo. Once I have that number, I can perform the calculation. I will search the web for latest population data of Tokyo, right? So this is something. What happened here was that this prompt that I gave was was given to the reasoning agent. The reasoning agent queried the GPT-4o model, which understands prompts, understands intent and meaning, right? And that particular model gave back the response that the user is asking for 15% of the population of Tokyo. So you need to figure out what the Tokyo's population is and then multiply it by 15%. It also returned an action that use the web search tool to find the current population of Tokyo. Thus, the next step the agent takes is actually going and searching the web for the newest and the latest information, which is an agent in itself, calling the web search with current population of Tokyo 2023. Once this particular query runs, it gets all the web search results that that particular agent returned in terms of what is the population of Tokyo. Let's just say document number one says that it is something like this. Document number two is going to say something else, right? It summarizes that, okay, and it gives it back to the LLM again to understand it. The LLM takes it, it understands what the token is. It also takes into account the context of the chat, that what the first prompt was, what was thought number one, what was action number one, and what I have got is actually the return of action number one. When with this much context, LLM processes all those tokens and gives back, okay, I found several sources confirming that the population of Tokyo is 2023. It's in 2023 is approximately this much. Now I have the population, I need to calculate 15%. And here we go. It again called another, here we go. It again called a new tool called the calculator to figure out 15% or whatever this number is. So The LLM itself is acting like a brain, while the agents are its hands, mouth, other things that you need to actually make sense of tasks and not only prompts. So both of these in conjunction becomes a new chatbot that we use to solve our problems, to figure out solutions, to plan our tasks, and everything else.
So let's bring it all together and connect back to where we started. Remember our visualization bank moved from financial words towards water words? Now you understand why. During training, the AI saw countless sentences with bank in different contexts. Each time it predicted poorly, backpropagation adjusted the attention weights. Gradually, the QKV matrices learned. Bank should attend strongly to the nearby context words like river or money, right? During inference, when you type your message, those learned weights activate. Bank queries for context, finds river, has a high matching key, pulls in river's value, the embedding shifts, the dot moves. The full pipeline looks like text goes to tokenize, goes to embed, add position, then attention and feed forward repeated for each layer, then output. Every component was shaped by training. Embeddings learn meaningful positions, attention weights learn what context matters, feed forward layers learn to refine representations. All from one simple objective: predict the next word. Nobody taught grammar, nobody defined what bank means. The AI discovered patterns that help predictions, and those patterns look like understanding. That's the pre-trained in GPT, billions of examples, trillions of weight updates, millions of dollars, all happening before you type your first message. Once it's ready for use, as we saw in the reasoning agent, it does way more than take your prompt and predict the next token. It breaks down tasks. Keep querying the LLM, uses its ability to use tools. Now, that's something that you should think about. So next time when you chat with an AI and it just gets what you mean, remember these dots moving through meaning space. Remember that this isn't happening in real time. The AI learned these patterns from billions of examples during training. Remember that 2017 paper, Attention is All You Need? That figured out how to train models to handle context. That's the transformer. That's the T in GPT. It's not magic, it's attention mechanisms shaped by training, simple math repeated at astronomical state. I will link this interactive tool in the description. Play with it yourself. Try any of the any of the simple prompts that you want to do. A word of note: I'm using Google 10K for my vocabulary, so you can't really use very complicated words. Keep it simple. Try to understand what it is doing. Thanks for watching. If this finally made training and attention click for you, like and subscribe. See you the next one.